In carrier sense multiple access with collision detection, we have a mechanism to detect collisions and to deal with or handle the collisions. In CSMA, there is no procedure to handle a collision. So if a collision happens, you don't know what to do. But this protocol, carrier sense multiple access collision detection, augments the algorithm to handle the collision. If there is a collision, the frame, so the policy is, if there is a collision, then resend the frame. Okay, so if a collision happens, then just resend the frame. So as we said before, if station A is sending a frame, it needs time to arrive at station D. You see here station C sends the channel at this point, because this frame at the beginning of this frame is not still here. C will see the channel as idle, and then it will start its data, because it sends the channel, it was idle, then it sent its data. Therefore, collision happens, it sends the data needs time to propagate. So here a collision happened. The collision will not be sensed immediately. So the first bit of collision to be sensed here needs time. This bit should travel until it arrives here. So here I detects a collision. Okay, so when it detects collision, it immediately stops sending the frame. Okay, and then will abort and then call the back of or maybe retransmits the frame. Okay, depending on the algorithm. So when a collision happens, it also needs time. So the collision will be sensed after this period of time. C will detect collision not immediately after sending, but after some period of time until this first bits of collision arrive here. And of course D will detect collision later. Here it will see there is a collision. So if we look at the algorithm, it's almost very similar to the multiple access, but we have a mechanism to deal with collision. So start with k equals 0. We use one of the persistence methods, one of these, either this or this or this, to sense the channel. Okay, so sense the channel. Okay, so depending on the persistent method, if you see that you have the right to send, then send the channel. Okay, no, send the data to on the channel. So when you send, either you have to see transmission done, that's the end of what you want to send, or there is a collision. So if it's a transmission is done, okay, you send your frame is done. Now you check collision detected. If there is no collision detected, means you sent your data properly. But if the collision detected, then go the following procedure. Now if the transmission is not complete, you continue send and receive. Continue until your transmission is done. So when you finish your transmission, you check if a collision is detected or no. If it's not detected, then you send your data successfully. But if a collision is detected, then send a jamming signal. So here, for example, collision happened, okay? This does not know yet that collision happened. This collision have to go back or go this way. So which one will receive the jamming signal? The collision first will know about the collision. C, because it's closest to the collision point. So C will send a jamming signal, okay? So D, B, A, all will receive the jamming signal. The jamming signal is to inform the other stations that a collision happened so that they stop transmitting their data. So when the collision is detected, any of these stations, any of them, if they detect collision, they will send a jamming signal to warn the other stations that there is a collision happening. And again, increment because you did one attempt and it was not successful. Now try if it's the maximum number. For example, in this case 15 attempts. If you did so many attempts and you were not able to send your data, then stop now. Try maybe after some period of time, because the channel may be so busy, so it's not convenient to send now. Now again, choose a random number R between 0 to 2k minus 1. This is a random number depending on k. K is the number of attempts. So when k is higher, the random number can go to, for example, 15, can go to 30, can go to 60. So when the attempts are more, this TB or wait time or back of time will be maybe probability to be higher. It still can be small, but can go to a very big number, because if you say 2 to 15 minus 1, this is a very big number, okay? So this is R, you multiply it by TP. So when the attempts are there are more attempts, there is a probability that this time can be longer, the wait time, okay? Because if the media is busy, then you may try after longer period of time, and then you apply again, sense the channel, apply one of the persistent methods, and do the same again. This is the carrier sense collision detection algorithm. There is actually a requirement for this protocol. It's a minimum frame size. For this is the minimum Ethernet frame, 64 bytes, came from this requirement. We'll see now why. For CSMA CD to work properly, we need a restriction on the frame size. Worst case scenario, where's the worst case scenario? If the two stations involved in a collision are the maximum distance apart. So in this case, let's say A and B. So these are the maximum distance apart. The signal from the first takes TP to reach to the second, of course. And the effect of the collision takes another TP to reach the first. So let's see here. If I sense a frame at TT1, it will arrive here after, of course, if we did this before. So this will be TP. I think we have it here. So this A sent a frame at T1. It arrived because there is propagation delay. It arrived here after TP. This is T1. This is T1 plus TP. Okay. So if, for example, collision happened here, just before this point, if a collision happened, this collision needs to be go to the other side so that it's sensed by. So another TP. Sorry, I'm not doing it properly. Wait, please. Okay, this is TP. And collision detected here, so it's at the end of this. So another TP until I senses the collision, because collision also is a signal. It needs to propagate, so you need 2 TPs to observe the collision. So if I was sending a frame, okay, and then a collision happened here, if the frame ended at this point, then I will assume that it sent its data properly without any collisions. And but actually a collision has happened here, and this data that I sent was damaged. So it should have waited until this point to check that there is no collision, no problem with data. So A should actually continue sending data for this time period, for 2 times TP, until it's sure that there is no collision. So this is the requirement. So the requirement is that the first station must still be transmitting minimum frame size after 2 times 2p TP. Because if it was not sending data, it will, at this point, for example, it was sending until here, and collision happened here. This collision needs time to arrive to this point, but at this point it has already finished its transmission, station A. So it doesn't care if because the transmission finished without receiving a collision signal, then it will assume that this frame was sent properly, but it was not, because collision happened here. So I should be sending data, still sending, until you have to wait this time until the collision signal arrives again. So another TP and TP. So the minimum frame size should be at least 2 times TP, because we have 100 meters maximum segment length in Ethernet, and this requirement will nearly translate to a minimum of 64 bytes minimum frame size for Ethernet. You can study, I think maybe we'll be back to this point again. So there is minimum frame requirement. There is another protocol which is used in still used in wireless networks, is collision avoidance, carrier sense multiple access with collision avoidance. In this protocol, we want to prevent collisions. The basic idea is that a station needs to be able to receive while transmitting to detect the collision. So to detect collision, you have to be able to receive while you are transmitting, because how you know if a collision happens? So when there is no collision, the station receives its own signal. So if you are sending a data and there is no collision, you are receiving your own data. When there is a collision, the station receives its own signal and the signal transmitted by second station. Okay, so assume two wireless links. So if these links, if this one is sending only, it will only receive its own signal, because this one is not sending. Okay, so it will only receive its signal. But if they are both sending, it will receive this its own signal and the signal from the other station, if they are both sending data. To distinguish between these two cases, the received signals in these two cases must be significantly different. Okay, so you have to either you are receiving your own signal, or your own signal plus signal transmitted by the other station. In a wired network, the received signal has almost the same energy as the sent signal. This means that in a collision, the detected energy almost doubles, as we said, because when there is the collision, the voltage levels will be almost double. But this is not true for wireless, because the power density is related to 1 over r square, which decreases very rapidly when the distance from the transmitter increases. So in this case, the signals will be different. In wireless, much of the sent energy is lost in transmission. The received signal has very little energy. Therefore, a collision may add only 5 to 2%, not doubling like in wired signal, additional energy. This is not useful for effective collision detection, because there is noise, there is other factors. So 5% increase in the signal may not be accurate indication that there is a collision, not like in wired networks, because the energy will almost double if there is collision. Carrier sense multiple access collision avoidance was invented for wireless network because collision cannot be detected and should be avoided. Therefore, because collision detection is not accurate in wireless network, this protocol has been devised to prevent collisions at all, to prevent collisions happening. So this is collision avoidance. Collisions are avoided through the use of 3 strategies. So we have interframe space. When an idle channel is found, the station does not send immediately. So even if a channel is idle, no one is sending, you will not send immediately. You will wait for a period of time called IFS, interframe space. Even though the channel may appear idle when it's sensed, a distant station may have already started transmitting, because you don't know, maybe someone else already started transmitting, but you didn't receive its signal yet. Therefore, you wait IFS before sending. Contention window. The contention window is an amount of time divided into slots. A station that is ready to send chooses a random number of slots as a wait time. If it finds the channel busy, it does not restart the process. It just stops the timer and restarts it when the channel is sensed as idle. This gives priority to stations with longest waiting time. Acknowledgement with all these precautions, there still may be possibility of collision. Therefore, the data uh, should be acknowledged. If data is received correctly, you send acknowledgement so that the sender can know for sure that its data has been delivered. Because even though you are trying to prevent collisions, but collisions can happen. But there's also the possibility that data, because it's wireless, there is a possibility that data may be corrupted during transmission, not because of collision, but because of other interference. Or so acknowledgements are also important factor in carrier sense multiple access collision avoidance. So if you see the timing in this protocol, you sense the channel continuously. If you find it idle, you see it's busy, so sense continuously. So like the one persistent method. If it's idle, don't send immediately, but wait for IFS. Okay. So now you have the contention window, which is the number of slots. You see, these are slots. It's not just these slots. You have a random number of slots. Then after that, you send the frame and wait for timeout. So if we look at the algorithm, you see here k equals 0. You have data to send, so k equals 0. It sends the channel. Is it idle? No. Sends, continuously sends until it's idle. If it's idle, don't send immediately, but wait IFS, interframe space period. Okay. Now you check again. Is it idle? If it's idle, you can go to the next step, but if it's not, go to the first step. Now it's idle. Choose. You are not going to send a stall. Still not going. Choose a random number, r between 0 and 2 to power k minus 1. Okay, and then wait r slots. So here we sensed and it was idle, but we are not sending yet. We'll wait these number of slots. So r random number between 0 to 2 to power k minus 1. So when these slots expire, then you can send. After the slot timer ended, send the frame. Now wait timeout. Timeout is what? The time, of course, for you to send and receive acknowledgement. So if acknowledgement is received, that means you did successfully. But if it's not received, because either there was a collision at some point, or because the acknowledgement itself damaged or corrupted, or because the data was corrupted because of noise of interference, then if the acknowledgement is not received, increment the k and check if you did maximum number of attempts or not. If not, go to the beginning and try again. So this is about the random access method. If we go to the beginning, we said we have these categories. Okay, so we studied these. Now we have also the controlled access methods. These ones are three methods that we study: reservation, polling, and token passing. Could you please send me your names in the... So we have the other method which is called the control access method. In this method, the stations consult one another. In random access, there is no controller. You just, everyone is, all the stations have the same role. There is no difference. But here, they have to consult one another to find which station has the right to send. We have these methods: reservation, polling, and token passing. So in the reservation method, you see here, a station needs to make a reservation before sending data. Okay, so station 1 wants to send data. It has got this, the time is divided into intervals. Okay, so this is in each interval a reservation frame. This is the reservation frame, precedes the data frame. So before sending the data, there is a reservation frame. So in this reservation frame, station 1 tells the it wants to send data, so it will set the flag to 1. Station 2 don't have anything, so it's 0 in this slot. Station 3 has data, and station 4. So before sending data, this control frame is sent. So now a reservation frame, this is which is a control, precedes the data frames sent in the interval. For n station, if you have 5 stations, you need 5 mini slots. So these are mini slots. Okay. The reservation frame, in the reservation frame you have, this is the reservation frame, you have to have 5 mini slots. If you have 10 stations, you have to have 10 slots. When a station needs to send a data frame, it makes a reservation in its own slot. So this slot is for station 1. It has some data to send, it will flag it as 1. The stations that have made reservation can send their data frames after the reservation frame. So now station 1 has data to send, it will send its data because it has reserved. Station 2 cannot send, no, because it has not reserved a slot. Okay, but station 3 will also can send, and station 4. Okay, and so on. So next reservation frame, only one has got data to send, so it will set the flag to 1. So now station 1 can send. This method is called control access method. The other method is polling. Polling works with topologies in which one device is designated as primary station. So this is like server, and the others are slaves or secondary stations. All data exchange must be made through the primary. So any data exchange should go through this device. The primary device controls the link. The secondary device follows its instruction. So if the primary wants to receive data, okay, if it wants to receive data, it asks the secondaries if they have anything to send. This is called poll function. Okay. If the primary wants to send data, it tells the secondary to get ready to receive. This is called a select function. So we have pull and select. Now let's see here. Primary wants to receive data, so it will ask A or send it a pull. Do you have data to send me? NAC, negative acknowledgement, means A tells the primary that it doesn't have any data to send. Okay, now it will pull B. Pull if data it has got data. So we're talking about the pull. So if the primary wants to pull B, it will send pull. Then B has got data, it will send its data. Then the primary will send acknowledgement to B to tell B that it received its data properly. This is the pull function. In the select function, the primary will ask select one of these stations. For example, here it selects B. B will acknowledge the primary. Yes, I'm ready to send data. Now it will select it and data. So primary wants to send data to B. It will send it as select. Are you ready to receive data? The secondary will acknowledge yes. Now it will be selected and the primary will send its data to B. If data is received correctly, the secondary will acknowledge to the primary. So it will tell it that it received its data correctly. There is another method. This is the most important one. We'll study some topologies. It's called token passing. In token passing method, stations in a network are organized in a logical ring. You remember we studied the physical ring. Here it's a logical ring. Logical means it may be a physical star, okay, like a hub or a switch, but it works like a logical ring. Okay, so we have two topologies, logical topologies and physical. Physical topologies as you see them. How? For example, if you have switch and stations connected to it, this is a star topology. But this star topology can work as a ring topology. Let's discuss this and you'll understand it. So stations in a network organized in a logical ring. Okay, for each station there is a predecessor and successor. So predecessor and successor. For example, for station A, predecessor is, for example, C, and is if the token passing is this way, so C comes before A, B comes after A. So you have a predecessor and a successor. So the successor of A is B. If the token passing was this way, of course it can be other way also, depends. So each station will have a successor and predecessor. The current station is the one that is accessing the channel. So if station A is accessing the channel, it's the current station. The right to this access has been passed from the Of course, C, for example, before it was the current station, but it finished its work or sending data, then it passed the write to station A. Now station A controls the channel. Okay, station A controls the channel. It will keep hold of the channel until it finishes its transmission or data that wants to send. Now it will pass, there is actually a control frame called token. It will pass the token to the next station, in this case station B. So the predecessor for A is C, the successor is B. So this write will be passed to the successor when the current station has no more data to send. So the successor is B. When you have no more data to send, pass the write. How you pass the write is we have actually a special packet called token. So it's like anything you think that gives you the authority to control the channel. So when the token A holds the token, it can control the channel, it can send the data. But when it has no data to send, it will pass the token to B. B now controls the channel, can send the data, no one else can send. Okay, so it will send its data. When it's finished, it will pass its the token to C. So the token will circulate in this direction, okay, always through the ring. The possession of the token, which node has the token, gives the station the right to access the channel and send its data. So if you don't have the token, you cannot send data. You can listen, but you cannot send. When a station has some data to send, it waits. So if C has data to send, the token is with A, it cannot send. It have to wait. A will pass the token to B. If B don't have any data, it will pass it to C. It will not pass it back to A. It should go in this ring direction. If the ring, okay. So it should wait until it receives the token from the predecessor. For example, here B is predecessor for C. It then holds the token and sends its data. When the station has no more data to send, it releases the token, passing it to the next logical station in the ring. The token must be monitored because sometimes the token may get broken or corrupted, okay? So you have to ensure that it has not been lost or destroyed. Because if it's destroyed, then no one can send. You have to have one station that have the token so that it can send data. Control access methods actually in the physical ring topology, when a station sends the token to its successor, the token cannot be seen by other stations. The successor is the next one in line. For example, here the direction. The problem with this topology is that if one of the links medium between the two adjacent stations fails, the whole system fails. So if this link fails, the whole system fails. If this, so any of these links if failed, we normally use dual ring topology, okay, which uses a second ring which operates in the reverse direction. So one this direction, the other one this direction. If one of the links in the main ring fails, the system automatically combines the two rings to form a temporary ring. After the failed link is restored, the auxiliary ring becomes idle again. The high-speed token ring networks, FDDI, if we can, maybe we'll have and CDDI, Copper Distributed Data Interface, uses this topology. So either because the tokens any link, if it fails in this ring topology, if any of these links fail, the system will fail. But here, if one link fails, the system can use the other ring to until the damaged link is corrected. You see, this is a bus ring topology. It's physical bus, but logical ring. This is a star ring topology. So it's a logical ring, but physical star topology. So in the bus ring topology, also called token bus, this token bus or bus ring, the stations are connected to a single cable. This is the bus, called the bus, and make a logical ring. So even though it's a physical bus topology, the logical topology is a ring topology. Each station knows the address of a successor and predecessor. The token bus LAN, standardized by IEEE, uses this topology. We are not going to go to the details. In the star ring topology, this is the most common. The physical topology is star. So if you look at it physically, it's a star topology. There is a hub that acts as a connector. The wiring inside the hub makes the ring. The stations are connected to this ring through the two-wire connections. This topology makes the network less prone to failure because if a link goes down, if one link goes down, it will be bypassed by the hub and the rest of the stations can operate. Also, adding and removing stations from the ring is easier. This topology is still used in token ring LANs designed by IBM. So this is a star ring topology. This is a bus ring topology. Bus physical, ring logical. Star physical, ring logical. Okay, so that's it for today's lecture.